Section 4.4, Fundamental Theorem of Calculus. We have two objectives in this section. The first one is to apply the Fundamental Theorem of Calculus to evaluate definite integrals. And the second objective is to solve applied problems involving definite integrals. So up until this point in time, we've been evaluating definite integrals by looking at the area they represent, then either using geometry or Riemann sums to estimate the definite integral. But this will change with the introduction of the Fundamental Theorem of Calculus, because with this theorem, we can evaluate the definite integrals without looking at any graphs whatsoever. So the Fundamental Theorem of Calculus says this: if a and b are two real numbers and little f of x is a function, then the integral of the small function f of x from a to b is equal to the antiderivative of f of x, so this is what we call capital F of x, evaluated from b to a. So basically, all we have to do is find an antiderivative, then plug the upper bound into the antiderivative, and subtract from that the answer that we get when we plug in the lower bound into the antiderivative. And so we don't have to use graphs anymore. We could just evaluate integrals like we're about to do in example number 1 without ever having to graph or look at any pictures. So in example number 1, we're told to evaluate the definite integral. And sometimes the question will just say find or solve. Either way, we do the same process. In this case, the integral is going from 2 to 5, and we have the 2x plus 3 inside as the integrand. So how does it work? Well, first of all, what we're going to do is pretend like the 2 and the 5 don't exist, and we just deal with the 2x plus 3. So we're supposed to integrate 2x plus 3. We know there's a rule that says you just integrate the terms one by one. You can ignore the plus because of the sum and difference rule of integrals. So we start with the 2x, and we ask, what's the antiderivative of 2x? What's the function we differentiate to get 2x? Well, one way to do that is to just take the 2 and then add 1 to the power of x, so it already has power 1, so add 1 to that and then divide by the same value. So the 2x squared over 2 is the antiderivative of 2x, and obviously you can reduce it to lowest terms and write x squared, but for now I'll leave it alone. Next I have the 3, and what is the antiderivative of 3? So the antiderivative of 3 is just simply 3x, again using what we learned at the beginning of this chapter. So this is what we typically call the big f of x, and this is what we call the small f of x. Usually, we also add a plus c at the end, but we'll see in this problem that putting the plus c here is really not required because it's going to cancel out. Now, the extra new detail that we have to add is this little slash at the end and the 2 with the 5 afterwards. So basically, this notation is saying whatever expression is on the left side, we will put 5 into it first in all the places where there's an x, then we'll put the 2 into all the places where we see an x, and we subtract the two answers. That's what basically this notation is saying. So let's continue along. So let me first reduce everything to lowest terms. I'm going to put x squared plus 3x plus c, and then I'm still going to evaluate this between 5 and 2. So now let's go ahead and plug in the 5. So 5 is going to go in all the places where we have x. So we're going to get 5 squared and 3 times 5 plus the c. So 5 goes in first because it is the upper bound. It always goes in first. Then according to the rule, we are supposed to subtract basically the same thing again, but this time we're going to put 2 into all the places where we see an x. So we're going to put 2 squared plus 3 times 2, and finally plus the c. So why am I putting the 2 in? Because 2 is the lower bound, it goes second. And at this point in time, all I have to do is just square some numbers, multiply, add some things, and I'll basically be finished. So 5 squared is 25, 3 times 5 is 15, plus c. And then I have minus the 2 squared, that's going to be minus 4, minus 3 times 2, that's going to be minus 6, and finally minus the plus c is going to make it a minus c. Now remember, c is just some kind of a real number, so it's just a regular old constant, And the first thing I want to notice on this line at the end is that the c is going to cancel out the c ultimately. So this is why when I'm doing a definite integral, I usually will tend to skip writing the c, because why write it 1, 2, 3, 4 times when eventually it's going to cancel out anyway? We could just kind of ignore it right off the bat, and that way we save a little bit of notation. We don't have to write it down. Nothing is going to change in the answer. Now, ultimately, you're going to have some kind of a number at the end, and in this case, the number is going to be 30. You can confirm that by putting it into your calculator or just solving it by hand. So this 30 represents the value of this definite integral. Now, is it the area, or is it the net area? Is it the total area? We don't know because we didn't graph the function to x plus 3. So at this point, all we know is that the value of the integral is 30. And if we wanted to confirm whether this is the area or the total area, we would have to graph it to x plus 3 and look at the region from 2 to 5 to see if it's always above or below the x-axis, and then conclude whether the 30 that we got is the total area or the net area. So let's do this again one more time. In example number 2, we're going to be told again to evaluate each definite integral. So it's basically the same idea. We're starting off with the integral from -1 to 3 with 6x squared minus 4x plus 1 with respect to x. So again, we start term by term. We're going to evaluate the antiderivative for 6x squared. That's going to be 6x cubed over 3. Then we will evaluate the antiderivative for -4x. That's going to be -4x squared all divided by 2. Or you could just put the x squared over 2. It does not matter really. It's the same thing. And finally, the antiderivative of 1. The antiderivative for 1, it's just 1x. And you can just write x if you prefer. And basically, that's it. What I have to do next is tell myself a little reminder that this is the fundamental theorem of calculus. So I'm supposed to plug in the 3 and the -1 into the answer. So remember, this right here represents the little function f of x, and this over here represents the antiderivative, which we call capital F of x. So this notation says put the 3 in first, put the -1 in next, and subtract the answers you have. Let me first reduce everything to lowest terms to make life a little bit easy. So 6x cubed over 3, that's the same thing like 2x cubed. Then 4x squared over 2, that's the same thing as -2x squared. And finally, there's the plus x, and we want to evaluate it between these values. So according to the fundamental theorem of calculus, 3 goes in first into all the places we have an x. So we're going to start with the 2 times 3x cubed minus 2 times 3 squared plus the 3. So every time I see an x, I go ahead and replace it with the upper bound first. Then the rule says I need to subtract, and I'm subtracting multiple terms, right? So make sure you use some brackets or parentheses or whatever, and we are going to put the lower bound next. So the lower bound is -1, so go ahead and replace all the x's with -1. And at this point in time, you can do this by hand or you can use your calculator. It's up to you, it doesn't really matter. However you want to do it, it's fine either way. So 3 cubed is 27, times 2 that's going to be 54. 3 squared is 9, times 2 is going to be 18. And finally there's a 3 there. -1 cubed is -1, multiplied by 2 is going to be -2, but there's a negative in front of the whole thing, so that's going to make it +2 ultimately. -1 squared is going to be 1. 1 times -2 is going to be -2. But with the extra negative sign in front is going to make it back into +2. And finally, there's a -1 at the end, but it's also being negated. And so we get a +1 over here. And you can put all this into your calculator, and you'll see that this is equal to 44. So again, at this point in time, we don't know whether 4 represents the net area or the total area. So for now, we just know that the value of the integral is 44. And if we want to be sure whether this is representing the total area or the net area, we would have to plug it into a calculator, plug the f of x into a calculator, and look at the graph between the function, the values -1 and 3, and the x-axis, and confirm using the graph. Okay, so before I move on to the next page, let me show you how we can plug this into a calculator as is and confirm that our answer is 44. Now I'll be using the classic version of this, meaning the classic view. Sometimes your calculators will show something slightly different, but for me, I'm going to be using the classic view, so that way if somebody's using a TI-83 or an older generation TI calculator, they can follow along and apply the same steps to see that they get the same solution. So on the main screen of the calculator, so once you turn it on the main screen, you're going to click the math key that's directly under alpha, and you're going to scroll down a few times until you see option number 9, which says FNINT. I find it easier to just click the button arrow up a few times, and there it is. For me, it's option number 9. You may have more options, you may have fewer options, depending on your model of the TI that you're using, but I'm pretty sure that the TI-83s and 84s all contain this FNINT command. So once you see it, you're going to click enter. And what the calculator is expecting from you next is a few things. First, it's expecting the function that you see inside of the integral. So for me, that's 6x squared minus 4x plus 1. So that's the first thing that the calculator is expecting from you. Then you're going to use the little comma to add extra inputs. So the comma is the key directly above 7. Click that key, and what you're going to tell the calculator next is the variable you used on the first part. So I used 6x squared minus 4x plus 1. I used the variable x, so I'm going to tell the calculator I used x. Then I do another comma and give it the lower bound and upper bound, again separated by commas. So for me, the lower bound is -1, so make sure you use the tiny little minus sign to tell the calculator that the lower bound is -1, put another comma, and then add the upper bound, which is 3. And finally, we're done, so I'm going to close the parentheses and just hit enter. And as you can see, it will say 44. Now, the calculator is not programmed to do this unless you have a lower bound or upper bound. So this does not work for regular integrals. It only works for definite integrals where you have a lower bound and upper bound. If you're using one of the newer TI calculator where you have the nice, awesome math print, your commands will look like this. So you're going to, again, go to math and then select option number 9. And you can see it draws the integral, it puts the parentheses, it puts the d variable. So all you got to do is start by filling in the little boxes. Lower bound is -1, upper bound is 3, and then the function is 6x squared minus 4x plus 1. And you have to tell the calculator that you're integrating with respect to x. So the usual, then you hit enter and it will return the same value. Now remember, the calculator is not using calculus to do this, it's estimating this using some techniques that we don't need to get involved in right now. So sometimes you might see something like 39.999994 or something. It's not going to be always exactly on the spot. It all depends on the function that we're working with. So this is why it's preferable that you use the method by hand and then confirm using the calculator that your answer is very close to what you see on the screen of the calculator. Okay, so let's move on to part 2 of this example. So we have an integral going from 0 to 3, and we are integrating 4x plus e to the x with respect to x. So as usual, we have to integrate the 4x first. The antiderivative for 4x will be 4x squared over 2, because we add 1 to the exponent and we divide by the same value. The antiderivative for e to the x is simply itself, e to the x again. So there's not much for me to do there. And this is a fundamental theorem of calculus because I have the definite integral. I need to add the little slash at the end and remind myself that I still need to plug in the 3 and the 0. Now, before I actually plug in any of these values, let me reduce this first fraction to lowest terms. 4x squared over 2 is just going to be 2x squared. The e to the x is not going to change. And I'm still going to plug in the 0 and the 3. Every time I see an x, I need to replace it with 3. So 2 times 3 squared plus e cubed. This is what I get from plugging in the upper bound, which is 3. And again, I need to repeat the same thing with the 0. So 2 times 0 squared plus e to the 0. So keep in mind that because we have multiple terms that we're usually subtracting, it is very important that you add the second set of brackets. The first set of brackets here is not required because there's nothing in front of it, but I usually like to put it just to make it all look kind of similar. But this bracket and this bracket is really, really required because the minus sign in front of them needs to go to everybody inside the bracket. If you don't put the bracket, you'll remember to do it for the first one, but then you'll forget to do it for the second term, and that will make your answer completely off. So brackets are going to save your life here, so keep them in mind. All right, anyway, now it's just a matter of multiplying, adding, subtracting a few things. So 3 squared is 9, 9 times 3 is 18. E cubed is some random number, I don't know, I don't care. And 2 times 0 is going to be 0, so I'm going to put 0 there. And e to the 0 is really equal to 1. So this whole thing is just 1, but there's a minus in front of it, so I need to put a negative 1 at the end. So my final answer is going to be 17 plus e cubed, and that's the solution there. Now, again, since we have the calculator already turned on, let's go ahead and see how this would work on the calculator. So I'll go back to the original classic print, and let me start by plugging in math number 9 into the calculator. This gives me the fn9t command. This is expecting a definite integral. I'm going to write the 4x first, and then I'm going to add e to the x. E is in blue on the ln key for me, so I have to go second, then click the ln key to get e to become visible on my screen. I need to put the x variable, and I need to close the parentheses, so that way the power is basically finished. Then the next thing I do is put comma, tell the calculator the variable I used, then comma again, give it the lower bound, comma again, give it the upper bound, and then close the parentheses. So that's how it's going to look when you type it all in, and you're going to hit enter, and it's going to be a decimal on screen. So this is why this method, again, is not super acceptable, especially on quizzes and exams, because usually we want exact answers, but this method always gives us a decimal or something maybe that's not always useful because it's not the exact value. Now let me confirm that this is exactly matching with our answer by putting in the solution that we got and comparing the decimals on screen. As you can see, they're both the same. So 17 plus e cubed is more correct though, because it's technically the exact value. Okay, so let's move on to part 3. So in this problem, we have the integral going from 1 to 2, and it's 1 over x dx. So take a moment here to pause the video and see if you can solve this problem. It's not too difficult. It's a straightforward problem, but it uses a special formula that we learned about the antiderivative for 1 over x. So take a minute, pause the video, and then I'll solve it in a second. Okay, so what do we know about the 1 over x? So x is on the denominator, so usually we need to write the problem on the numerator. So we need to rewrite it like x to the negative 1. But x to the negative 1 dx is a special case of the power rule that requires ln absolute value of x as the solution. So usually the formula tells me to write down ln of x plus c. So this is the formula that I'm required to use typically when I'm dealing with 1 over x. Now, a few things. I'm still required to do it here in this problem. The only difference is I'm not going to write down the plus c, but I have to add the extra slash with the 1 and 2 because of my definite integral. So I'm going to ignore the plus c because I'm doing a definite integral. Instead, I'll write down the little vertical line and put the 1 and 2 next. So keep in mind again, this little guy here represents the small f of x. It's 1 over x, and this represents the capital F of x, which is the antiderivative of 1 over x. And again, we don't write the plus c because we're dealing with a definite integral. There's nothing to simplify here, so I'm just going to write down the answer. ln of 2 is the upper bounds value, and then ln of 1 is what I get from plugging in the lower bound. So upper bound was 2, so it goes in first in all the places where I see an x. and 1 is the lower bound, so it goes into all the places where we had an x. Now, ln of 2 is some random number, and I don't need to write down the absolute values anymore, so I'm just going to put parentheses, and that's because 2 is already positive. It doesn't need to have the absolute values around it. ln of 1, you may recall from another course or maybe from earlier in the semester, ln of 1 is equal to 0. So this is ln of 2 minus 0, which is, ln of 2. So my final answer is that this is supposed to be ln of 2. And let's confirm with our calculator. So again, math 9, I'm going to type in the 1 over x first, then put the x in, then put the lower bound, then put the upper bound. And again, it's going to be a weird decimal that becomes visible on the screen. That will not be acceptable as a solution because it's not the exact value. Exact value is ln of 2. So let me plug in ln of 2 and show you that they are exactly the same. So now let's read example number 3 together. It says find the area of the region bounded by the graph of y equal to x squared plus 1. The vertical lines x equal to negative 2 and x equal to 3 and the x-axis. So first thing what I'm going to do is graph this y equal to x squared plus 1. So I know it's a parabola. I know the vertex is going to be somewhere at 0, 1. So I know it's a parabola, so it's going to look something like a U shape, and it's going to open up towards the top part of the page. I have two lines that basically were mentioned. There's the line x equal to negative 2. So I'm going to pretend like negative 2 is here somewhere. So they want me to start at this location and end at the location where x is equal to 3. So let's pretend like this is 3 here. So we're going to basically stop there. And they want to know what's the size of the area bounded by the function, the x-axis, and these lines. So they want to know how much is that space over here. And so you can see this space is not a trapezoid. It's not a rectangle like we had to deal with in previous sections. It's kind of a weird, funky looking shape. So the only way to do this and get an exact answer is to use a definite integral with the fundamental theorem of calculus. So let me make this a little bit smaller so we can have more space. But now that we see what the graph looks like, we can tell that the function y equal to x squared plus 1 is always above the x-axis. So we can use an area equal to an integral going from the lower bound, which is negative 2, all the way to the upper bound, which is 3, and then write x squared plus 1, the function we want to integrate, with respect to x. So we know that this definite integral that we're going to evaluate is going to be exactly the area. It's not the net area, because the region we highlighted is always above the x-axis. So whatever answer we get, we don't have to do any changes to it. We don't have to add any absolute values to anything because the area is always above the x-axis. So we begin by integrating x squared. The antiderivative for x squared is x cubed over 3 because we add 1 to the power, then divide by the same number. Then the antiderivative for 1 is just going to be 1x. And if you'd like to write just x, that's fine too. We're going to add the little slash with the negative 2 and 3 to remind us that we're not done yet. We need to plug in the upper bound and the lower bound. Okay, so let's go ahead and do that. So 3 goes in first. We put in the 3 in all the places where we have an x. And the negative 2 goes in afterwards. So negative 2 gets cubed, divided by 3, plus an extra negative 2 at the end. So remember how this works. The upper bound goes in first, so the 3 is going to be first, and then the negative 2 goes in afterwards. For this, you can use your TI calculator to plug it all in, then hit it with a math 1 at the end to turn everything back into a fraction, but let's just do it by hand here. So 3 cubed is 27, but 27 divided by 3 is going to be 9. So far I have 9 plus 3 from the start. Then I have negative 2 cubed, which is negative 8, divided by 3. But there's a negative in front of the whole thing, so it's going to be 8 over 3. And finally, there's the minus plus negative 2. So plus negative 2 is going to be negative 2 total. And then an extra minus in front is going to convert it back into a positive value. So I get positive 2 there. So let's see, 9 plus 3 is going to be 12. 12 plus 2 is going to be 14. So I have basically 14 and 8 over 3 as my total. And so I need a common denominator. I need to basically put a 3 underneath the 14 and multiply the 14 by 3. So the total is going to be 50 divided by 3. And that's the n. So 50 over 3. So since we have a calculator, let's go ahead and use technology and use the calculator to confirm that our answer is correct. So there's a few things we could do with the calculator. First, on the main screen of the calculator, we are going to test out if our theory is correct. So we're going to click math and then option number 9 for f and i and t. We'll put in the function we're working with, x squared plus 1, comma x, comma the lower bound, which in this problem was -2, comma the upper bound, and hit enter, and it will be some kind of decimal. Now there are times when the calculator may be able to convert the decimal into a fraction, so let's test if that's possible for this one. I'm going to click math and then click option number 1, and this is going to take whatever answer I already have and try to turn it into a fraction. Sometimes it's possible, sometimes it's not. It just depends on the type of answer that you got. If your answer had a square root or something like that in it, or ln or e, it may not be able to convert it into a fraction. But in this case, it is able to do it. And that's because the answer we got, we already know it's a fraction. It's 50 over 3. So the calculator can convert it because the answer is, in theory, a fraction. So this is one option. The other option is to go to the y part of the screen and plug in x squared plus 1 into y1. Once you've done that, click zoom 6 to reset the window, and there's the parabola that we're talking about. And now we can click second trace to go into the calculate menu and choose option number 7, which is the integral option. The calculator is going to ask for the lower limit. This is -2 for us. So -2, hit enter. Then it's going to ask for the upper limit, which is 3 for us. So click 3, then enter. The region is highlighted, and you can see the full region is always above the x-axis, and it gives you the solution at the bottom of the graph. It says 16.666, and so on and so forth, which is exactly what we saw on the main screen, which we know is 50 over 3. So we can be certain that our solution is correct. So there's two different variations on how to do the problem. Ideally, you want to know how to do it by hand, but you can always use your calculator to confirm your results, and you'll know that you're doing things correctly. Okay, so now that example 3 is done, let's take a look at example number 4, where we have to find the average value of a certain function over the interval from 1 to 9. And so again, just as a reminder, the average value is something we discussed in the previous section. The average value formula is the formula over here. It's 1 over b minus a, integral from a to b of the little function f of x dx. So a and b are the lower and upper bounds, or the lower limit and the upper limit, lower bound, upper bound, however you want to call them. And so it's basically a definite integral. We can use the fundamental theorem of calculus to evaluate that integral, and we just have to multiply it by some kind of a fraction in front. Now, for this problem, the function that I'm working with is the square root of x plus x squared. This may be difficult to draw from memory because it looks nothing like what you may have come across before. So let's go to the calculator and plug it in here to see what it looks like. So square root of x is first. I need to close the parentheses, then add the x squared. What I care about is the interval from 1 to 9. So before I click on zoom and click number 6, I'm going to do something else. I'm going to click on window and just modify my window a little bit. I don't care to see all the way from -10 on the x coordinates because I only care about what's going on from 1 to 9. I'm just going to put 0 there, so that way 1 to 9 will be visible between 0 and 10. It's going to be smack in the middle of my screen, which is awesome. The other thing I'm going to do is remove some of these extra negative y coordinates. I don't necessarily need to see all the way from -10 on my y coordinates. I know that square root of x and x squared will always be positive in my interval from 1 to 9. So I'm just going to, again, change this to 0 all the way to 10. This may be too big or too small. We'll check in a second, and we might have to modify the y maximum, maybe change it to something bigger or smaller. We'll find out in a moment, but let's see what the graph looks like. Yeah, so it definitely seems like I don't see the full graph, because when x is equal to 9, if I try to trace x equal to 9, for instance, it will say 84. So the window that I chose is not super appropriate. The y coordinates are going all the way up to 84. So I need to go back to my window and change the y maximum to be something bigger than 84. So you can choose 90 or 100. That will be either way fine. But there we have it. So now we can see the full graph. So remember, we care about the region going between 1 and 9, and we want to know the average value of the function. So, okay, so the graph looks something like this. So we just have to kind of translate it to the page here. So I know it's going to look something like this, for instance. So I'm not going to be super picky about it. This is what my graph looks like. And my x equal to 1 is somewhere over here. My x equal to 9 is going to be somewhere over here. So I want to know the average value of the function between 1 and 9. And I know at 9, the value was 84 when I traced it. And at 1, the value is really going to be square root of 1 plus 1 squared, which is going to give me a 2. And if you want to confirm, you can go back to your calculator and just click trace 1, hit enter, and you'll see that the y coordinate is equal to 2. So, that's good. So now we know what we're dealing with. We know the shape of the function, but what we care about is the average value. So let's start by writing down f average. So this is the average value theorem, and it needs 1 over b minus a, integral from a to b of the function f of x dx. So this is just the formula that's listed on top, but what is a, what is b, and so on. So first of all, the a and b are the upper and lower bound. So for me, the upper bound is the b, which is going to be 9. The lower bound is the 1. And what is the function? The function for me is this guy over here. So that's how we're going to fill that up. So it's 1 over 9 minus 1 times the integral going from 1 to 9. And it's a square root of x plus x squared with respect to x. So this is the thing that we're calling the average value. So to color code it all, the 9s are first because they're the upper bound, then the lower bounds, then finally the actual function itself. Now let's continue. So the average value is going to be 1 over, basically 9 minus 1 is going to be 8, so we can just write 1 over 8 there. And we have an integral from 1 to 9. I can't integrate it yet because the square root of x is not written in the right form. We need to have x to a power. So just remember that the square root of x is x to the 1/2 using a formula that we talked about previously. Why is it 1/2? Because there's a 1 here and an invisible 2 on the outside. So the 1 on the inside goes in the numerator and the 2 on the outside goes in the denominator. So square root of x is really just simply x to the 1/2. And x squared, I don't have a problem with that yet, so it's going to wait for a little bit while we rewrite the square root of x. And now we are ready to find the average value. Average value is 1 over 8 times, okay, what's the antiderivative for x to the 1/2? I'm supposed to add 1 to the power, so it's going to be 3/2. 1/2 plus 1 is going to be 3/2, and technically I got to divide it by 3/2 also. But we said this is inconvenient, it adds too many details and too many steps, so instead what I'll do is I'll just multiply it by 2/3. So I'll just directly multiply by the reciprocal of the second fraction, and that gives me 2/3. The other thing I need to do is find the antiderivative for x squared, which is going to be x cubed over 3. Now remember, the integral had a 1/8 in front of it, which means everybody that I get from the integral needs to get a 1/8. It needs to be multiplied by all of them. So make sure you put the brackets around the answer. And remember, we're going from 1 to 9. So now it's time for the fundamental theorem of calculus to take over. And what we got to do next is put the 9 into all the x's, then put the 1 into all of the x's. So we'll start off with the 9 first. And so the average value of the function f, f(avg), is 1/8 times 2/3 with 9 to the power of 3/2 plus 9 cubed divided by 3. So this is what I get from plugging in the upper bound value, so 9. And I need to subtract next the 1/8 and plug in the 1, so 2/3, 1 to the power of 3/2, plus 1 cubed over 3. So that's basically how we apply the fundamental theorem of calculus here. Now, this is kind of tedious to evaluate by hand, so I would recommend that you just whip out the old calculator and punch this whole thing into the calculator. You can try to do it by hand. For instance, this part over here, it's saying 9 to the 3/2. That's the same thing as the square root of 9 with the power of 3. So one way to do it is just find the square root of 9 first, which gives us a 3, then cube it, and you'll get 27. And then you'd have to multiply by 2 divided by 3 afterwards, and so on and so forth. It's not terribly difficult to do it by hand, but we have TI calculators that can evaluate these things, so why waste our time? But when you punch this whole thing into the calculator, you should be able to see 65/2 as your final answer, which is the same thing as 32.5. So my final answer is 32.5. So what does this mean? Let's talk about what the meaning of all this is. So first of all, this area that I'm working with is kind of a funky looking area. It's got 3 sides that are basically horizontal or vertical, right? There's the bottom, it's horizontal. There's the sides 1 and 9, they are vertical lines. So there's 3 vertical sides, but this side over here is kind of not vertical. It's not horizontal. It's a little bit curvy. So if I wanted to convert this area into a rectangle that starts at 1 and ends at 9, right? So if I want to convert the orange area into a rectangle starting at 1, ending at 9, where would I need to put my rectangle? How high would my rectangle need to go? Would I need to put it here? Would I need to put it there? Or would I need to put it there? So that the area within that rectangle will be the same as the original area. And so it turns out that according to this calculation that we did, the place where you want to place it is around 32.5. You want your rectangle to be as high as 32.5. And so now within this rectangle, the area contained will be identical to the area that we started off with at the beginning. That's what this means. That's what the significance of the fundamental theorem of calculus is. So the area in green here is equivalent or equal to the original area that was in orange, but the benefit of this is the area in green is just the area of a rectangle rather than a weird looking shape. Now, as you can see, the rectangle crosses my curve, and if you want to know at what point in time would the crossing happen, what's the x value where this occurs, I have some information about that below in the little paragraph, and you can see that the x-coordinate where that happens is around 5.49. So let me show you what this whole paragraph is saying by going to the calculator and seeing how to plug everything in and what you're doing, basically. So going to my calculator, first of all, let me evaluate the integral we care about. So I'm going to first show you the region that we were interested in. The region was starting at 1, ending at 9. So this is the region we care about. And so let me do this next. Go back to the Y menu and put in 32.5. Oops, 32.5. This was our average value. Let's look at the graph. Now we have the horizontal line. And let's click on, again, second trace. and click option number 7. Lower limit, I want to be on the red curve first, and the lower limit is going to be 1, and the upper limit is 9. And so you can see this is 260, just like the previous one said 260. So they both contain the same area. Now what I'd like to know is the intersection point. Where does the red line cross the original red curve? So this line and this curve have some kind of intersection. So where is the intersection happening? So let's draw them without all the extra shading. To know where the intersection is, we can use the calculate again and select option number 5 for intersect. So option number 5 basically allows me to find the intersection of two curves. So my calculator is asking for the first curve. You can pick either the red one or the blue one, it doesn't matter. It's selecting the blue one already, so I'm just going to click enter. And it's asking for the second curve. I only have two curves, so it automatically jumps to the second one and says, is this the second curve? I'm going to say yes, hit enter. And then it wants to guess. So it's asking me, can I guess the answer? And obviously I want to say yes. So I'm going to hit enter one more time on my keyboard. And there it is. You can see at that location, the x coordinate is 5.491, so approximately 5.5, 5.5 approximately. And the y coordinate is 32.5, just like our average value. This is all again listed over here. It's not really a requirement for you to know how to do all this, but we've done all the steps previously in different sections, so it's kind of nice to put them all together in one place and see the reason why you are learning all those previous details. It's kind of nice to see it all together in one place, contributing towards a greater goal. But if I went too fast, you can either rewind the video or just take a screenshot of what this paragraph says to be able to do this on your own. Okay, so let's talk about some applications. So all these applications, or the next few applications that we're going to do, are going to again use the fundamental theorem of calculus in one way or another. And in example number 5, it says, suppose a bug moves along a straight line with velocity given by the velocity function 24 minus 3t millimeters per second. So this is how this function is describing the velocity of the bug that's moving along a straight line. Now this is only valid between 0 and 8 seconds, right? That's the time interval. We know it's in seconds because of that unit right there. So the velocity is being measured in millimeters per second, so I know that the time is also going to be in seconds. So they want me to find the average velocity of the bug over the time interval 0 to 4. So only part of the interval, not the full time 0 to 8. Then again, do the same problem, but find the average velocity from 4 to 8. And they want us to put some units on our answer, so we'll worry about that when we get there. But first of all, let's try to answer the average velocity on the interval 0 to 4. So the average velocity, first of all, let's remind ourselves that the velocity function is 24 minus 3t. So what's the average velocity? First of all, I'm going to write v average, and it's just an integral with 1 over b minus a in the front. The integral is going from a to b, and the function that I'm working with this time is called v of t, so I'm going to be integrating it with respect to t. So I'm using t's because that's what the letter is in this problem. The independent variable is t, not x, so everything has to be in terms of t. For this part of the problem, remember that the lower bound is going to be 0, and the upper bound is going to be 4. So the velocity average is going to be, the average velocity is going to be 1 over 4 minus 0, integral from 0 to 4, and we have 24 minus 3t with respect to t. This is equal to 1 over 4, because 4 minus 0 is going to be just simply 4. And remember where I'm getting these numbers. This is the lower bound, and this is the upper bound. And this v of t is the original function that was provided to me in the problem. I got it from here. Let's integrate the 24 next. The antiderivative for 24 is 24t. And let's integrate the 3t next. The antiderivative for that is 3t squared, all divided by 2. Now keep in mind that both of these have a shared 1/4. It's supposed to be in front of the whole integral. So they both need to be multiplied by 1/4. And the way I say that is I put the parentheses around them. And this was a definite integral after all, so I need to add the extra notation, 0 to 4 there, to remind myself that I'm not done yet, that I need to plug in those upper and lower bounds. So remember, upper bound is 4, and lower bound is 0. So what's the average velocity of this bug? Well, it's 1/4, and 24 times 4 first, minus 3 times 4 squared over 2. This is what I get from plugging in the 4 in upper bound. And I need to subtract from that, again, 1/4 multiplied by 24 times 0 minus 3 times 0 squared, all divided by 2. So this is the value that I get from the lower bound. And again, you can decide to do this by hand or using your calculator. It's up to you. But, 24 times 4 is going to be 96. So we have 1/4 times 96 minus 4 squared is 16. 16 divided by 2 is going to be 8. Then 8 times 3 is going to be a total of 24 minus all of this is going to be just 0 because 24 times 0 is 0. 3 times 0 squared over 2 is going to be 0. So this whole thing here is just 0. So I need to subtract 0 from the 96 minus 24 thing. Anyway, this is going to be 18. Now, it needs a unit. So what unit are we going to be using? Well, we are talking about average velocity after all, and velocity is measured in millimeters per second. So the average velocity is going to be, again, measured in millimeters per second. So that's my final answer for part 1 of the problem. Now I need to redo the whole thing all over again using the second interval, but now that you've seen part 1 being done with the interval 0 to 4, I'd like you to take a moment to do the other one on your own, and I'm not going to go through it all, but I'll just give you the final answer, and so you can confirm whether you did it correctly or not. But pause the video here and solve the second part of this problem where you're looking for the average velocity from 4 to 8. So just like before, the velocity function is the same. So most of the work is going to be the same. The integral is going to result in the same expression when you integrate it. The only difference is the upper bound and lower bound are now 8 and 4. So when I plug everything in and do my calculation, I'm finding out that the average velocity on the interval from 4 to 8 is 6 millimeters per second. So hopefully you can confirm that your answer is also correct and you got the same thing. If not, then maybe we should talk in office hours, or maybe you can repeat the problem and see where you made a mistake. Maybe you forgot a parenthesis somewhere, or minus sign did not get distributed correctly, or maybe you mixed up your upper and lower bounds. But at this point in time, this should be standard procedure. You should be able to find the average velocity of the bug, and hopefully you got the correct solution.